So now that you know how to draw organic molecules, let's refresh you on how to name them. Now there's a systematic naming system that was put together by the International Union of Pure and Applied Chemistry, and that's the one that you use at A level, and by and large that's the one we're going to use throughout your course, although there are a lot of trivial names, acetic acid instead of ethanoic acid for example, that you'll also need to recognize. But the nice thing is now for you people, you lucky people compared to people like me, is that we've got drawing software, ChemDoodle, that you'll use in the first couple of years, and then ChemDraw that you might get to use as a third or even a fourth year student, in which you draw the structure and it will name it for you, because of course it is a very systematic naming system, which means that it's relatively straightforward to automate it. Now here's an example of a molecular name, a very colourful example. So let's just quickly go through the bits of this. Okay, the end bit, in this case the ol, right, is called the suffix because it goes at the end. And that's the dominant functional group, as we're going to go through, and in the next video I'll actually detail this quite significantly and put you to sleep. Different groups have different priorities in terms of the naming. And if you've got more than one group in a molecule, well then the more dominant one is the one that leads to the suffix. Now the infix, which is a word I've never used before in my life until I started taking the slides that my colleagues had used previously for this class, and they're putting the infix in there. Well, anyway, that tells you about the unsaturation of the main chain. Now, of course, unsaturation, how many double, triple bonds do you have? And so if there's no double or triple bonds in the main chain, then that's an from the alkanes. If there's a double bond in the main chain, then it's N, and if there's triple bond, then it's in for alkynes. And of course, N comes from alkenes. Then you have the parent, that's the length of the number of carbons in the main chain. That's of course what you're very familiar with. And then finally the prefix, as opposed to the suffix, pre coming before. This can be all kinds of things depending what other substituents you've got on there, functional groups, positioning of those functional groups, whether or not it is a cyclic molecule, and so forth. So let's start talking about the hydrocarbon bit, the boring bit. It's going to lead to the chains and the rings and so forth in our molecules. You count the number of carbons the way organic chemists count, and you should know those: metheth, prop, bute, pent, hex, hept, oct, non, and dec. Now, of course, if there's no functional groups, it's a really boring type of molecule. Alkanes, and their name ends in ane. Where you name them, of course, is the longest chain. So here's a nice simple one. There's 4 carbons in that, so it's a butane. If you have branches, you always name those branches using the number of carbons in the branch and then ending it with YL. That goes in the prefix. So this molecule, for example, here, longest 4 carbon chain is a butane, and then we have the 1 carbon bit coming off there, so that is a methyl group. And although in this case it's unnecessary, you always need to number where things happen, and so in this case that will be on the 2nd carbon, thus making it a 2-methyl butane molecule. The reason, of course, that I hope you appreciate that it's not actually crucial in that particular case to put the 2 in is you cannot have any other type of methyl butane other than the 2-methyl butane, but we'll come on to more of that later on. Staying on the numbering, of course, you always use the lowest possible numbers where you can. So in this particular case here, I could number from the left, 1, 2, 3, 4. I could number from the right there for that other molecule. Both of those would be ways to depict 2-methyl butane. What I would not do, of course, is start for this molecule here, the way I've drawn it, start here and go 1, 2, 3, because the lower number will be to start at that end and go 1, 2. You've got more than one group. So for example, this molecule here, well, there we've got 2 methyl groups, 1, 2. Again, you can see it comes off of our butane, and those methyl groups will be on carbon 2 and carbon 3, making it 2,3-dimethyl butane. And then, of course, if you've got more than one group, so example, this one here, Longest chain there is of course an octane, and then we have a methyl group there, 1 carbon with the YL, an ethyl group there, 2 carbons with the YL. Those appear on the 3rd and the 4th carbons respectively, and then when we put them in the name we do it alphabetically by the group, so E will always come before M, and so that becomes a 4-ethyl 3-methyl octane. Trivial stuff for you all, huh? So all that stuff should have been totally review from your previous studies. And I debated whether or not to put this particular slide in, but I thought, what the heck, why not? Because organic compounds don't stop at 10 carbons. So if we go higher than that, here's 11 through 19, pretty much as you might expect. 10 is decane, and so 14, for example, 4 and 10 tetradecane, and so forth. Do notice that we're not using a meth, eth, prop, beautiful 1, 2, 3, 4. We're back to what you might expect. Then we get to 20. 20 in Greek is eikosane, and then notice the funky weird thing that we're putting in here. 21 is not uneikosane, it's hene-eikosane. Okay, so after we get past 20, 1 just becomes hene again. So 1 could be meth, it could be un, it could be hene, and so on. But anyway, after that 30, the tricontane, 40 tetracontane, so that contane is now what we're using in terms of 10 carbon atoms, so pentacontane, hexacontane, heptacontane, etc., all the way up to 100, which is hectane, and then you kind of start again almost. So 110 is not decane, it's decahectane, 10 and 100. So you can build up names like this, and I don't know if I'm going to bother to put things like this on an exam. I might put them on a quiz, I might put them on an exam. It really depends kind of on how I'm feeling the day I set the exam, but just in case, let's name a few funny ones that you'll never ever see in your life. We've got 71 carbon atoms in there. Well, 70 is of course heptacontane, 1 is that funky hen, so hen heptacontane. 97, well, 90 is nonacontane, 7 is hepta, so hepta nonacontane, and then 118 octadecahectane. Now, something that I definitely need to remind you of is the word homologous, as in homologous series. So homologous series are molecules that have the same fundamental formula. So in the case of alkanes, that's CnH2n plus 2. I hope you've seen that before. So if for a regular alkane, if you've got n carbons, then the number of hydrogens, multiply it by 2 and add 2 to it. You've probably already seen abbreviations when we write out molecules and so forth, but here are some really important ones that you need to know. So an example of using an abbreviation for methanol here, we would say, instead of saying CH3OH, we just replace the CH3 by ME, because our abbreviation for methyl or methyl is ME. Thus, it doesn't take much intelligence to realize that ethyl will be ET, propyl will be PR, and butyl will be BU. There's a couple of ones that, I'm kind of introducing things before I should, but I'm going to. If you've got a benzene ring as a group attached to a main chain, then you use phenyl for that. Abbreviation is PH. Frequently confused by students with where you got a benzene ring and then a CH2 that goes on the ring. That's a benzyl group, and so you can abbreviate that BZ. Again, what a benzyl group is a phenyl group with then a CH2. Now, those are very appropriately allowed by the IUPAC. Interesting, also allowed are old-fashioned names applied to groups. So this group here, if you see it, here's the main chain, and then we got a 3-carbon chain coming off it. So you'd say, well, it's a propyl group, except that instead of it being bonded at the end carbon there, it's bonded at the middle. So this isn't a propyl group, it's an isomer of a propyl group, thus called isopropyl, or abbreviated either iso-PR or a little I in italics and a superscript beforehand, PR. Same idea with this. This is a butyl group, 1, 2, 3, 4, but we would call it an isobutyl group because it's an isomer of a butyl group, and appropriately abbreviated like that. There are 2 other common, well, semi-common, one's very common butyl groups that you'll see. It's this one here. Again, you can see it's 1, 2, 3, 4, so it's a butyl group, but it's attached here by a secondary carbon, so we call it sec-butyl, and there you can see the abbreviations. And then the last one of my favorite groups in the whole world. Again, it's a 1, 2, 3, 4 carbon group hanging off, so it's a butyl, but here the main chain is bonded to a tertiary carbon, so it's called tert-butyl there. Now, I know at A level you learned that these sort of had other funky names to them. You will so rarely see those other names when we can use isopropyl, sec-butyl, and so forth. So now the last in this alkane hydrocarbon bit boring video, we'll talk about the cycloalkanes. That's an alkane that's got a ring of carbon bonds. So cyclopropane, there we are, cyclobutane, cyclopentane, one that we're going to study ad nauseam next week, cyclohexane, and then of course cycloheptane, cyclooctane. These are all fun to draw, especially when you have drawing programs that give you the shape straight off. Notice that these are again a homologous series, but in this case the formula is CnH2n. We've lost 2 hydrogens from the alkane homologous series, and the reason for that is of course that we've actually got an extra carbon-carbon bond by joining the ends of the chain together to make a ring, and anytime we have a new carbon-carbon bond we remove 2 hydrogens. Remember that, we'll be coming back to that idea here. So you can see here, for example, there is pentane, C5H12, cyclized in this case, so we've got that extra bond between the way that I've drawn it, the red and the pinky carbon atoms, so now it is C5H10. More in the next video.